All right. So let's go through these and see how we did. All right. So letter A. All right. What does it look like we should shoot for here for letter A? What kind of test should we use maybe? Okay, so we're going to use limit comparison, and yeah, we're going to compare it to a P series. Okay, so we'll compare this to, say, n squared over n to the fifth, yeah, which is the same thing as 1 over n to the third. Okay, 1 over n to the third does what according to P series? Converges. Okay, P is greater than 1. All right, and so by limit comparison, we would expect this to converge as well. Okay, now I can also go through, remember we should technically be doing the limit comparison where we also check to make sure that the limit of the ratio of those series, so the 6n squared plus 17 over the 2n to the fifth minus n cubed plus 5n, and then divided by this, but instead of dividing, we're going to multiply by the reciprocal, so n cubed over 1, right? That's going to give us 6n to the fifth over 2n to the fifth. As that goes to infinity, we're going to get 3. Okay, and so check, our L is finite and over there. Right there. Thank you for getting it. Our limit is finite and positive. And so we know then that the behavior of this series will mimic the behavior of this series, converge, right? So there it is. Okay. All right, how about letter B? What should we be shooting for here? Okay, so another comparison, and we can use, this case, it's going to be comparison to a what? Geometric series. Okay, so our geometric series, again, I'll say verses here for the comparison part. We'll compare that to 2 to the k over 5 to the k, or in other words, 2 over 5 to the k. Now, 2 over 5 to the k, geometric, and we know it does what? Converges because r, the absolute value of r, is less than 1. Okay, and so we expect this thing to hopefully then also converge. But again, we want to show that limit comparison, or the limit as n approaches infinity, of this, the 2 to the k over 3 plus 5 to the k, and I'm going to, again, instead of dividing, I'll multiply by the reciprocal of 5 to the k over 2 to the k there. All right, so again, you can see the 2 to the k's are going to cancel right away easily. The 5 to the k's, if you work through L'Hopital's, you'll see that eventually you're going to end up with 1 there.
So when would we use the less than?
So converges. Sorry?
2 to the k over 3 plus 5 to the k is less than.
You could also use a direct comparison in that case too. You could say it that way.
3 plus 5 to the k is not less than.
3 plus 5 to the k will be less than this. Because you're adding 3 to the denominator. Yeah, 5 to the k, yeah.
So why is it less than?
Because you're adding to the denominator. So the numerators will be are going to be the same value, right? But the denominator is going to be 3 more, so it's a little bit smaller because you're dividing by a large number. Exactly right. So you could also use, direct comparison here. So yeah, either one works. Okay, but I would really say, the direct comparison, don't worry too much about that one. The limit comparison really is, where we're going to put the basket we're going to put our eggs in, okay, as far as that's concerned. So, all right, how about letter C? Diverges by? Okay, so we can compare it to a P series. I think you're right. That's a little bit fuzzy here, but we can compare it to a P series if we want. So let's see, that's going to be, again, from... we're going to have compared to the n squared over the square root of n, which we could say then is really 1 over, n to the negative 1 over n to the negative 3 halves, I guess, something like that. Okay. All right. Which then, if we're going to use the p series with the negative numbers, and again, the negative p value there makes me a little nervous, but it does diverge. Okay. I know that, and this does diverge too, as a result then. Okay, because again, if you set up that limit, it's going to work here. Did anyone use a different test here for letter C besides limit comparison? Yes, Sean? Use integral test. So integral test will work here too. Yes, if you integrate, again, the limit as b approaches infinity here from 1 to b of this. So maybe you didn't use P series, but so we're still going to use a comparison here, but maybe you didn't want to use P series. You could also just integrate n to the 3 halves, okay, and see what the behavior is that way, dot, 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 you'll end up with, it's going to diverge. It's going to go to infinity as well. Did anyone use a different test? Nick? Nth term test for divergence works here, right? The limit of this thing as n approaches infinity is infinity, which is not equal to 0, so nth term test for divergence would also show it diverges there, okay? So, again, you guys are going to have to develop, kind of in your own mind how you want to do things. Maybe you want to, preferably just stick to, always using that nth term test first, just to make sure, because it's so quick and easy to kind of like see if something diverges. But, oftentimes we do see it's going to go to 0, okay? In fact, in this case, for example, letter D, we can quickly see that this is going to go to 0. The limit as n approaches infinity of this sequence would go to 0 because the denominator's got a bigger degree. So we can't use nth term test here, or it would be inconclusive, I should say. But we can compare it, right? And we can compare this one too. Okay, another p series is going to be n to the 1/2 over n squared, which is the same thing as 1 over n to the positive 3/2 now. 1 over n to the positive 3/2, we know that what? Converges because p is greater than 1. And so therefore we'd expect this to also converge. Okay, and again, I'm not going to go through the limit stuff there. You can check that on your own to make sure it does. But it is. Okay? All right, how about letter E? What can we do here? Compare it to what? It's another p-series comparison here we can use. Yeah, so we can say, like, it doesn't have to be 2n. We can just say n over n to the 6th, which is the same thing as 1 over n to the 5th. 1 over n to the 5th, that what? Converges. Okay, because again, p is greater than 1. And so we'd expect then this to also converge. Okay, now, remember here, these limit comparison tests, there are some stipulations, right? We can't just like apply it willy-nilly, right? First of all, both our original series and the series that we are comparing both have to be positive, okay, for all their values. So if we alternate, for example, positive to negative, can't use limit comparison, okay? If you have some negative values or whatever. Also, again, we got to make sure that we compare, but again, we really should be also checking that limit to make sure that the limit as n approaches infinity.
When you say the negative values, what do you mean? Like which part?
So like none of these terms in here should be negative. None of these terms, when I from counting from 1 to infinity, no matter what n I put from 1 to infinity in here, these should all be positive, and so should these also be always positive.
So the negative 3/2 and C, that doesn't count.
So that's a negative 3/2 exponent.
Okay.
Any of the n's you plug in, will be positive, and then to the negative 3/2 will still be positive. So you're good to go there. Okay. But we also want to make sure anytime you're doing these limit comparisons, you should really just check to make sure as well that the in this case, for example, that 2 to the n over n squared plus 5 to the 3rd divided by the other series, or again multiplied by the reciprocal here, okay, will result in I guess I could have just done n to the 5th over 1. Let me just do it that way, it'd be easier. Okay, you can see here we'll end up with an n to the 6th, so it's going to be a 2, and we'll have an n to the 6th here times 1, so it'd be n to the 6th, so it's going to be 2 over 1, so this just goes to 2. So again, check, we have a finite positive number there, so it works. Whew. Okay, last one here, multiple choice, A, B, C, or D. Ooh, okay, silence. So, which of the following series cannot be shown to converge using the limit comparison test with this series sum from 1 to infinity of 1 over n squared? So in other words, right, okay, this is what we're going to compare it to. Which one of these four cannot use this as a comparison? Well, let's take a look at letter A. Could we use 1 over n squared to compare to this series? Yeah, we could, right? Because we have no n up here. Our highest degree down here is n squared, and so that's not going to be the one we want there. Okay. What about this one right here? Well, it's n to the 4th in the denominator, but it's under a square root, so we would really count it as a what? N squared. So we have, again, a 1 over an n squared there, so not that one. Okay. Now, for this letter C here, it's a little bit funky, but so like it's like, well, we see a sign of 1 over n squared. It's like we haven't really seen the trig show up here, but let's check something with this. So what do we know? If we're going to use limit comparison, right, it's not just like mathemagicking out that 1 over n squared. We have to make sure that the limit as n approaches infinity of our ratio of our sequences here, okay, we want that to be positive and finite. All right, well, if we plug in infinity here, I'm going to get a 0 here in the denominator, right? Infinity in here, I get 0 in the denominator, so we get a 0 there. And then if I plug in infinity here, 1 over infinity is going to go towards 0. Sine of 0 is 0. We get 0 over 0. Indeterminate form. We'll apply L'Hopital's. Okay, and then the derivative of sine is cosine, and let's call this not 1 over n squared. Let's say that's n to the negative 2. It'll just make it a little bit easier there. So cosine of n to the negative 2 times the derivative of n to the negative 2, so negative 2n to the negative 1 over, or wait, I'm sorry, negative 3. Subtract 1, Mr. Wade. All right, and so then derivative of n to the negative 2 here. Again, this is n to the negative 2. So let's say again negative 2n to the negative 3. Okay, the negative 2's will cancel, the negative n to the negative 3's will cancel. As we approach infinity here, that's going to be 0. Cosine of 0 is 1. Okay, so 1 indicates that we can use this here as a comparison, right? It works, right? We get the limit to be 1. It's finite and positive. And so not that one. We want something that's not going to work, and that's this guy right here. Okay, and here's the issue with this. If you take that ln over n squared and compare that to 1 over n squared, okay, and take the limit as that approaches infinity, well, instead of dividing by 1 over n squared, let's multiply by the reciprocal, ln n over n squared times n squared over 1. What happens here? The n squareds cancel out, and you're just going to plug infinity into natural log of n, and it's going to go to infinity, yeah, which is not what we want, right? So that's why D fails there. Okay, it fails the part where if you put them in a ratio, they don't equal a positive finite number. Alrighty? So that was a little bit, again, so you can see here, there's an example of kind of like, while, sometimes you will get, 2 minutes for an individual problem, a problem like this, you have to consider 4 things, okay, to get through it. And so, want to be quick with these. Okay, we want to be quick. Okay, moving on now to alternating series. So far, the majority of the series we've dealt with have had positive terms. Okay, now we're going to look at series that have both positive and negative terms. The most basic of these series is known as an alternating series. Okay, in other words, where the terms and the sequence alternate in sign. So, for example, we have this like seemingly geometric series here. Okay, and in fact, it is geometric, right? But then if we take that negative 1/2 out, we can say that's okay. It's negative 1 to the n times 1/2 to the n. And so we're going to end up, well, our first few terms, let's see here. So we're starting with n equals 0. So negative 1 to the 0 will be positive 1. 1/2 to the 0 will be positive 1, so we get 1. Okay? And then we have 1. Now we go to n equals 1. Our next term here, it'll be negative 1 to the 1 will be negative 1, and then 1/2 to the 1. So it'll be minus 1/2. Okay? And they're just going to keep multiplying by 1/2 here. So plus 1/4 minus 1/8 plus 1/16. Okay, so on and so forth. Minus 1/32, and then ... Okay. So this little thing in front here, they call this the alternating term, right? It kind of like shows that jumping from positive to negative every other term kind of deal. Okay, alternating term. Okay. But what do we know about this particular series? We can actually determine the convergence or divergence here. It will what? Converge or diverge. Okay, so what's our common ratio here? What are we multiplying by every time? Okay, so you can think 1/2, Or you can also think, Mr. Wade, what about this negative 1/2? Couldn't you say you're multiplying by negative 1/2 every time? Yeah, you could be right there too. Okay, so in fact, this is what we really want to consider here. So our R here is really what we're multiplying by every time. Each term gets multiplied by that negative 1/2 every time, right? Times negative 1/2 times negative 1/2, and so on and so forth. So our common ratio here is going to be the absolute value of negative 1/2, which is still less than 1, and so converges by a geometric series. Okay, converges by... Oh, convergence by geometric series. Okay, so that one we could do, even though it was alternating, okay, because we could make it a nice geometric series there. But that won't always be the case, right? So what do we do here? Well, enter the alternating series test. So the good news is, right, the alternating series test kind of gives it away, because you're going to see something like this, -1 to the n, or you're going to see -1 to the n plus 1, or -1 to the n minus 1. Okay? All these, the differences here that you see, it all just depends on whether you're starting with a positive term or a negative term first. So for example here, if n equals 1, is my first term going to be positive or negative? It'll be negative, right? Assuming a sub n is positive, right? So it says right here, over here, sorry, I should say. A sub n here is positive, right? So we're assuming a sub n is positive. So if our first term there is starting at 1, then yeah, we're going to have negative, and then it'll switch to positive, and then negative, and then positive, and dot, dot, dot. You get the idea. Okay. Whereas over here, with the way these are described, bless you, what are our terms going to be here? Where they'll start where? Positive, right? Because you plug the 1, it'll be 1 plus 1, so 2, -1 squared is going to be positive, and then negative, and then positive, and then negative, and then so on and so forth. You get the idea. Okay. So, should you have an alternating series like this, where a sub n by itself is always greater than 0, but then then you have the alternating pieces in front there, these will converge, okay? Converge, and that IFF stands for if and only if both of the following conditions are met. Okay, so this is for convergence here. The limit as n approaches infinity of a sub n is equal to 0. Okay? Because what happens if the limit as n approaches infinity of a sub n is not 0? We know it's going to diverge because of the nth term test for divergence, right? Okay, nth term test for divergence there, right? Okay, so we can see that, okay, potentially there, yeah. Okay, or if it goes to infinity, I should say. If it goes to a finite number, we still have to be careful, I should say. But if it goes to infinity for sure, it will diverge. So I should be careful with that. Yeah. Okay. So I do want to be careful. So if limit of, I'm going to put that in here. If limit is n approaches infinity of a sub n goes to infinity, or negative infinity, I'll say plus or minus infinity there, okay, then we know diverges. I want to be careful, because if the limit is n approaches infinity of a sub n is a finite number, it still might converge there, so I want to be careful because of the alternating piece. Yes, Kara?
So after the a sub n equals, what is that? Is that what it means?
Yeah, plus or minus. Plus or minus infinity there. Oh, here, I'll just rewrite it. Okay, and that's not super important for right now, but anyway, I'll just throw that out there. Okay, then diverges. Okay, but if we eke a finite number, yeah. All right, so that's the first condition. Again, this is the most important thing, right? We want to learn these conditions right here for sure, okay? Limit as n approaches infinity of a sub n equals 0 to determine convergence there. And then the other one is we just want to show that a next term is less than its immediately preceding term, okay? So like the next term in the sequence, or the next term in the series, must be less than the previous term. So we want to show that essentially that the sequence is decreasing as we go, right? Okay, so the key question here, right? And so again, these two things need to be in place to show convergence. So why do we need these two things? Well, this first one, okay, why we need this first one here to show the limit as n approaches infinity of a sub n is equal to 0, because we want to add values, okay, that get smaller and smaller. And alternate in sign so that the sum will be small. Okay? If we're trying to show convergence, right, and we're continually adding smaller and smaller numbers, well, that helps to get that convergence, right, because we're adding smaller numbers. But then it also helps even further if those smaller numbers are then alternating, because then those positives and negatives will kind of cancel each other out and make that sum smaller still. right? Make the sum even smaller still. Okay. And so that's why we need that first piece. And then for the second piece, why we need that second piece, well, let's start with an example here of a series. We'll just kind of make something up here, okay, with a purpose. Okay, so I'll make up this series that alternates, right? I mean, you can see here we're changing from positive to negative to positive to negative to positive to negative. And so we have an alternating series, and we can also see here that is the limit as n approaches infinity of our sequence here, is it getting closer to 0? Like, are these values getting closer to 0 as we go? Yeah. They are. They're getting smaller. So it's like we have what looks like an alternating series, positive, negative, positive, negative, positive, negative, right? And we have this condition, but do we have this second condition here? Is the next term always going to be less than the previous term? Well, next term is -1. That is less than the previous term. But then here, the next term, positive 1/2, that's not less than the previous term, right? Positive 1/2 is, again, the first term here. The next term is negative, so okay, the negative term will be less than. But again, you can see it doesn't quite work. So our second condition fails here. Okay, so it's like we're alternating. We have this first condition, but the second condition fails. Do we have convergence still? Because it looks like it's getting smaller, and we're adding these positive and negative numbers. Well, the way we can describe this series is using 1 over n minus 1 over n squared here. Okay, and I'll use a different color to kind of indicate that. So if we have, for example, if you see here, we have like 1 over 1, okay, and then we have 1 over 2, and then 1 over 3, and then plus 1 over 4, and that's coming from this 1 over n piece right here. Okay, compare that, though, to minus 1 over 1, minus 1 over 4, minus 1 over 9, minus 1 over 16, and that's coming from this minus the 1 over n squared piece right there. Okay, so while we kind of like created this alternating series whose values are diminishing, okay, it's not going to be quite enough to show that we have convergence here, because what do we know about 1 over n? What does that do? It's going to diverge, right, because p is equal to 1 there, okay? So this diverges to infinity minus then, what does 1 over n squared do? Converges, right, because p is greater than 1 there. And so converges to some number L. Now, if you take something that's infinite and you subtract something that's finite, what do you end up with? Infinite still, right? And so overall, this thing is going to diverge. Okay, this will diverge. Question?
For number 2, even if it was like one that actually worked, doesn't it still go positive, negative, meaning that the next term would always be greater than if it was a negative?
Say that again, sorry.
So like, say like it goes from like 1, I don't know, I can't come up with the top of my head, but if you're saying that it goes from negative to positive every single other term on a normal one, right?
Or positive to negative, doesn't matter.
Yeah.
You can start with the negative term or start with the positive term. Yes, an alternating series will alternate, yes.
Wouldn't the term after the negative value be greater than that value?
Oh, I see what you're saying. Sorry. So my apologies then. I'm sorry. You're right. Yes. So what I should have said here. So it's just the sequence that we're comparing here is what I should say. So the actual term. So sorry. You're right. We should be ignoring the signs here. My point then would be that, for example, here if we just think about this as 1 and this is 1, obviously those are not less than, right? But then also like here, yeah. Let's see here. 1/3 is greater than 1/4, for example. So there's another situation where the a sub 1. You're right. I'm sorry. Yes, and don't include the signs for those when you're comparing them. Yeah. Okay. So, long story short here, why do we just go through that? Because again, you see that both of these conditions are necessary, right? We need to show that, of course, this makes sense because we just need to show that those individual terms are going to get smaller and smaller and smaller, and the alternating helps, okay, so that the sum gets small, right? And then number 2, just showing these terms diminish, we also need to show this, though, because we can still have divergent series where we have decreasing terms and alternating as well. Okay? So we need to show that that next term is less than the previous term, kind of thing. All right? Note that sometimes alternating series are hidden or appear to be alternating but are not. For example, okay, this and this, okay, they look alternating, but why aren't they alternating? Yeah, we see that negative 1 is going to be squared, right? No matter what you put in for n here, you're going to have 2 times that n. So twice an odd number is even. Twice an even number is still even. So this is going to be always being raised to a positive even power. And so it's going to be, you know, positive, 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 so on and so forth. Same thing here, right? Okay, no matter what you put in here, what's going to be the case? It's going to be all negatives, right? Negative, 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 negative. Because anytime you take a number, multiply by 2, and then subtract 1, well, you're making it even, and then you subtract 1, that guarantees it's odd. So you'll have negative 1 to an odd power. Okay? So both of these are not alternating. Okay? They are not alternating. What about the other one here, though? Is that alternating? Yeah, it will be. Okay, we're going to take 1 times 3, so it'll be 1, 3 minus, 1 times 3 is 3, minus 1 will be 2, but then you put in 2, 3 times 2 is 6, minus 1 is 5, and so, you know, you're going to have even odd powers alternating there, so it is alternating. Okay, and then finally, very important here, this test cannot determine divergence. Okay, this test cannot determine divergence. You'll have to, you know, won't be able to do that. Only if it converges. If we don't match those things, it'll be inconclusive. All right. So, again, we're going to determine the convergence or divergence of the following series, okay? So, let's take a look. And again, I'll put our little properties up here. So remember, we're looking for the limit as n approaches infinity of a sub n to equal 0. And the second term to be, well, sorry, the next term to be less than the first term here. A sub n, not 1. Okay, there you go. Okay, so letter A. Is this an alternating series or is it not an alternating series? Indeed it is. Okay. We're going to take the limit as n approaches infinity. And again, when we take the limit as n approaches infinity, we ignore the alternating part. We're just going to take the limit as of the, you know, the sequence there. Okay, the non-alternating part. Okay. So again, because alternating, use alternating series test. Okay. So 2 conditions we have to check that we meet. Do our terms approach 0? Is the limit of this as n approaches infinity, is it going to be 0?
Yes.
No, yes, yes, no?
Yes.
Yes. Okay, the degree of the bottom is bigger than the degree of the top. The bottom's going to get bigger faster. Okay, so it goes to 0. Okay. Let's check now whether the next term is going to be less than the previous term. How can we do that? Well, we know our kind of like our, maybe we'll say our a sub n, that's literally just 11 over n plus 4, right? How can we represent a sub n plus 1? It'll be 11 over the quantity n plus 1 plus 4. Or in other words, it'll be 11 over a plus 5 is less than 11 over, why did I say a? N plus 5 or n plus 4. Okay.
It's true.
Okay, right. Is this going to be true?
Yes.
We have our numerators the same, but the denominator of what we want to be of we're saying the lesser one is greater. Then yes, it will be true. Okay, this is true. So what can we say about the series then? It what? Both of our conditions are met. It converges. Right? That is what determines for our alternate series. So it converges. Okay. All right. Letter B. Are we alternating here? Okay? Go ahead and take 30 seconds and come up with the series that this is. Okay. $15 seconds. Yeah. Time.
No.
Looks beautiful.
Question on that?
Yeah, what's the exclamation point for?
Let's exclamation point because it's n factorial. So we're going to now evaluate here. We do have an alternating series, so the limit as n approaches infinity of, again, just our sequence. We're going to ignore the alternating part, n plus 3 over the n factorial. Does this equal 0? N factorial, I mean, you're going to go to like infinity here, and you're going to multiply by all the numbers that are less than infinity together, whereas this is going to be infinity plus 3. So this is like infinity times infinity minus 1 times infinity minus 2. So this definitely is going to go to 0, right?
Suppose we can't determine it.
It goes to 0. Yes, Kara.
I don't really understand how that goes to 0.
So you have n plus 3. So imagine plugging infinity in here, right? You're going to have infinity plus 3 on the top. And then you're going to have infinity times infinity minus 1 times infinity minus 2 times infinity minus 3 times dot, 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 all the way down to 3, 2, 1. It's going to be ginormous in the denominator.
So you can have like a bigger.
But infinity.
So I would say yes, because it's like because it's like infinity times infinity times infinity times infinity. I know you're gonna have like the little minus 1, minus 2, but those again, it's
It's still infinity on the top.
correct. But infinity times infinity, much bigger, right? In the same sense that when you see like n over n squared, okay, we say that in this case the denominator is gonna get bigger faster because you're multiplying infinity times infinity here as opposed to just infinity. So yes, infinities can be, I don't know if I want to say greater than each other, but they'll get like bigger faster,
Wait,
I
so
guess
the
I'll
bottom
say.
one goes zero?
The
Up there.
this one
The
also
n
would go to
squared?
0 too. This one would go to 0. This would go
But
to 0.
when doesn't it? When there's n's in both the.
N squared.
Well, for example, this
Well, yeah, but like,
or this.
so is it always when the denominator is gonna have a bigger infinity?
Yes, 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 yes. If your denominator gets bigger faster.
Remember the problem? What problem was that?
Well, if you look back to find it, and I'll be happy to discuss that one. But yeah, and maybe it's but if your denominator gets bigger faster than your numerator, you're going to go to 0.
The problem where you tried to tell me that that was the case and I was against that.
Okay, so we have to go to the next section, the next term here. So a sub n plus 1, is that less than a sub n, right? That's our next question. So we'll go ahead and write these out. So let's see here. We'll have n plus 4 in the numerator over n plus 1 factorial. Is that less than n plus 3 over n factorial?
Exercise 7B.
Okay. So now, here the numerators aren't exactly the same. This numerator is 1 bigger than this numerator, and so you might be like, well, Mr. Wid, we added 1 to the numerator, but we're also multiplying the denominator by an additional n plus 1. Okay? Remember that n plus 1 factorial is n plus 1 times n factorial there, right? And so while, yes, we're adding 1 to the numerator, we're multiplying the denominator by an n plus 1. So that's going to be even more there. And so we would expect, yes, this to be true. Okay? And so then we'll say series converges. Okay? Questions on that? Okay. So why don't you guys go ahead and run through this one, okay? At least check your conditions and stuff like that. Let's just check the first condition, okay? So just check that first condition. Okay, just check that first condition here. Okay, check that first condition
Because.
and see what happens. Did you figure it out?
Yeah, it
Okay.
was 6 to the k over k squared. Plus k.
Aha, and so you see the difference
Yeah,
there.
so now I see why it makes sense.
Yeah. So good. I'm glad you brought that up. So yeah, that one would go to infinity then. Okay. Remember, when you do that first condition that you're checking, right, you can drop the alternating stuff and just.
Can you put the other one up in the meantime?
Oh yeah. You're welcome. Okay. Okay. So, after evaluating just that very first condition in letter C, what can we say about this particular series in letter C? It's going to diverge, okay? So the alternating series test is inconclusive, right? When you take the limit as n approaches infinity of that sequence, okay, alternating series is inconclusive. But because we see that each term is going to grow towards infinity, and we're just going to be alternating between positive infinity, negative infinity, positive infinity, negative infinity, we can say that it's going to diverge by the nth term test. Okay? I'm off the screen. There we go. Okay? Diverges there. Diverges, okay? If the terms in your series are approaching infinity, right? If the terms in your series are approaching infinity, adding a positive infinity, adding a negative infinity, it's still diverging because it's just it's infinite kind of thing. Okay. If you're adding, subtracting, positive, negative, finite values, well, that's a different story. Adding, subtracting infinities, infinity plus infinity, or infinity minus infinity doesn't necessarily cancel out. Okay. So anyway. All right. Last one here. Letter D then. Okay. Letter D. All right. So. Is this alternating? It's kind of hard to see, but we can rewrite this a little bit. Okay? In the denominator, we can rewrite negative 3 to the k minus n to be instead negative 1 to the k minus n times 3 to the k minus n. Okay? We kind of separate the negative and the 3 there, right? We can put them together, right? We did that in the past in the same exponent, okay? Or if you like, alternatively, you could even say k equals 1 to infinity, and we could say k over 3 to the k minus 1 times negative 1 to the k. Okay, this also, k minus 1, sorry. Okay, this also will work, because the reciprocal of negative 1 is still negative 1, so it's going to be the same there regardless, okay, of where you have it. It's important for us to pull that alternating piece out because when we go to do our components of the test here, we have to like leave out the alternating piece, okay? And so we don't want to just leave out the negative 3, right? That 3 is still part of our series, but that negative 1 k minus 1, that's the alternating piece. So you can kind of ignore it, right, and just evaluate the limit as k over 3 to the k minus 1 approaches infinity, okay? Which, by the way, what does this limit as k approaches infinity? What does that approach? Well, it's going to be infinity over infinity to start out here, which will apply L'Hopital's. Okay. And so the derivative of k is 1. Derivative of 3 to the k minus 1 is 3 to the k minus 1 times natural log of 3. Okay. Which then this will go to what? 0. Okay? And again, maybe you could see here, okay, well, if it's k versus 3 to the k minus 1, you would see, well, Mr. Wade, can't we just say from here that the denominator is going to get bigger much faster? And yeah, you could have if you wanted to there. But also, L'Hopital's works, just to show it there. So check. Okay? And then does our next term, is it less than our previous term? Well, again, the next term is 1 more in the numerator, but it's also 3 times as much in the denominator. So, yes, this holds true still, and so the series converges. What just happened? What's the question? Did I skip too much? Yes, Kara.
I'm confused on like how you set up part 2.
Part 2. So all we're doing here, when we set up, again, it's our next term, which is a sub n plus 1. So I'm just plugging, well, I guess k plus 1 in this case, right? So I just put in k plus 1 in the numerator, because the next term would be k plus 1, so it'd be k plus 1, and then 3 to the k plus 1 minus 1. And so the plus 1 and minus 1 just become 3 to the k. You see that, okay? And then the previous term would just be k over 3 to the k minus 1 kind of thing. Good on that now? Okay, yeah. And you're okay with the fact that the next term is less than the previous term?
Yeah.
Okay. All right. Let's move on then, because we still have quite a bit to cover. Okay, so turns out there's kinds of convergence. Hooray! More things to test. So we have absolute and we have conditional convergence. And actually, these you'll see here what the idea is here. Okay, so conditional convergence, right? Conditional convergence. That means the convergence of this series. Okay, the convergence of this particular alternating series is conditional on something. Okay, what is that? The idea is if the alternating series converges, but if you remove the alternating series part, and then that remaining series diverges, we call this conditionally convergent. This thing is convergent, conditional on having this alternating piece. Okay? So we say the series converges. We do, can do that kind of thing. But then if we get rid of that -1 to the n and see that, well, now, if we get rid of the alternating piece, now this thing is going to diverge, we say then this thing is conditionally convergent. Okay? All right, so let's check this out here and see what I mean by that. So we'll do the alternating series test again, because this is alternating, right? All right, so go ahead and do that. I'll let you guys run through that, okay? Check the alternating series there. Check to see that it, will converge according to alternating series. Remember, you can drop the alternating part when you're evaluating those limits, right? Just checking to see. So check. Okay. So it converges, right? Surprise! All right. In order to show conditional convergence, you have to be able to show that it converges in the first place, right? If we're trying to show conditional convergence, we have to be able to show convergence in the first place, or else it doesn't matter, right? Okay. You can't show conditional convergence if it's not convergent in the first place. Okay. So now let's check for conditional convergence. Question, yes.
How did you get rid of the -n? -1 via?
The idea is when we are doing our parts of our alternating series test, Mike, when we're doing our parts of our alternating series test, the components,
Yeah.
all we're comparing is just the sequence itself. We drop the alternating piece. So all you evaluate is the alternating, or is the non-alternating part. So
Like, I don't know how you split that up.
what's the alternating piece here? It's just this. So if I get rid of it, what's left? A 1, and then cube root of n is n to the 1/3. That's all I got to do. That's it. Make sense? Okay, so conditional convergence. Well, now we're going to check the limit, or sorry, not the sum from 1 to infinity of the absolute value of -1 to the n over the cube root of n. Okay? Well, if we take the absolute value here, what's going to happen to this alternating piece? It goes away. And then absolute value of the cube root of n, well, it's going to be cube root of n still because all of our n's are positive here. And so we can kind of just rewrite this series then as 1 over n to the 1/3. Now, what do we know about this series, 1 over n to the 1/3? It is a p-series that diverges. Okay, p is less than or equal to 1 there. So, with the alternating piece in place, our series converges. Without the alternating piece in place, our series diverges. So, our convergence is conditional on that alternating piece. So it converges conditionally. Okay, converges conditionally. Okay, so if we know something converges conditionally, we know it must converge, right? We know it must then also converge, right? A conditional convergence means the alternating series definitely converges. A conditionally converging alternating series means it must, just like on the basic sense, the alternating series converges. Okay, let's look at absolute convergence. Alrighty, so same principle here. Go ahead, evaluate the alternating series. Go ahead, take like 2 seconds there, figure that out. Okay, so hopefully you got this thing to converge. Okay, limit as n approaches infinity, 1 over n cubed, 0. 1 over n plus 1 cubed will certainly be less than 1 over just n cubed, because again, our n's are positive here. So let's check the absolute or conditional convergence. Again, we'll take the absolute value. Okay, we'll essentially get rid of the alternating piece and just consider the series without the alternating part to it. Okay. Now considering this series, how can we test for its convergence or divergence using the what? It's a p-series. Okay. P is now greater than 1, so that means this thing does what? I'll assume your silence means convergence. Okay, so since the alternating series converges and the not alternating series converges, then we know this converges absolutely. Okay, converges absolutely. Okay, so on to the back. There's some practice. Get cracking. We got a few more minutes here. I don't know if we'll be able to get them. We'll be able to review them, but let's get to them here. I'm going to give you about 5 minutes, and then we'll use the last 5 minutes to go over them, okay? So try to be speedy here. You've got 5 questions. That's roughly a minute a question. I know that's less than what you normally would get, but give it your best shot. Yes? Okay. Give about 5 minutes. 5 minutes. And feel free to go. Oh, there's 6 questions here. I can't count. There's 6 questions here. But anyway, I'll give you 6 minutes then. And you may use any test you want. Okay, any test you want.
Was it a two exclamation point or an exclamation point?
And exclamation point. There isn't one, but you can still determine the limit of that series if you need to. Because, so what's going to get bigger faster? Taking infinity times infinity minus 1 times infinity minus 2, or doing 2 times the solid infinite number of times. So, let me try.
An exclamation point.
Yeah, exactly. So if you think about like 2 to the 5th over 5 factorial, like, because that would be like a representation of it. You're talking here 5 times 4 times 3 times 2 times 1 over 2 times 2 times 2 times 2 times 2. So you see this, like these are always going to be larger, then you do the same, and then you have 1 versus 2, but still, because of all this previous stuff, definitely the factorial will outpace the exponential.
So it goes to 0.
So it's going to go to 0. Or no, it's going to go to infinity, because the numerator is going to go bigger faster. So since the limit is not equal to 0, we know that's going to. Exactly. Yes, I see you're spelling it exactly right. Yes. Okay. What's that? Correct. Exactly. Alternating piece. Same idea. You can remove that as your alternating piece there. Yeah. So, no, what I mean is like all of cosine n pi, that's your alternating piece. Remove that, you just have 1 over
So I'm feeling
your
it.
square root there. Exactly right. Yeah. Alternating pieces contain all in that cosine. So you just remove that. So yeah, just a little hint for letter B that cosine n pi, that's your alternating piece, right? Cosine n pi is your alternating piece there. So that's the part you can remove when you're doing your analysis there for that one. Okay. And remember, you're checking for convergent or divergent, but if it's an alternating series, you also want to check whether it's absolute or conditional there. Absolute or conditional.
So if it's negative 1 to the n, you can just count that as 1, or just cancel it, like don't count it.
So for your analysis, you need to check. You want to like ignore that part and just focus on.
Like,
So you want to ignore this piece and then focus on taking the limit as n approaches infinity of this, and then also do the check whether the second term is less than the first term. Okay. Check that the second term is less than the first. Or sorry, not the second term. The next term is less than the previous term, kind of thing. about 2 or 3 more minutes. Okay, we'll stop there. Well, not stop, but we're going to go over things. Here we go. Letter A. Should have gotten diverges. Woo. Okay, diverges there. Numerator gets bigger much faster than the denominator will, and so it's going to go to infinity. And since we're alternating between positive and negative infinity, okay, divergent. Okay, letter B. Converges conditionally. All right. It's P series when you check it out, right? That P series that diverges, but since the alternating series converges conditionally. Letter C. Also converges conditionally. Same principle here. Okay, we have, when you simplify it, so this one you have to rewrite a little bit, okay? Cube root of n, or n to the 1/3, n to the 1/2, and then bring that n to the 1/3 down, it becomes 1 over n to the 1/6. Okay, does go to 0. The next term is less than the previous term, so we do converge, but by the P series there, again, eliminate that alternating part, by the P series it's going to diverge, so again, converges conditionally. Letter D, converges. Yeah, that one's a little bit of work. Converges conditionally. Okay, you have to. You can use the integral test there. Okay, you can use the integral test. That one, because you let u be the natural log of n, then your du will be 1 over n dn, and so we'll end up with a natural log of the natural log of n, and then evaluate that from 1 to b. Put in infinity. Natural log of infinity is still going to be infinity. Natural log of the natural log of infinity is still be infinity, so it diverges. So again, we have converges conditionally. Okay, converges conditionally there. You got it. Good, good, good. Okay. All right. Which of the following series is absolutely convergent? All right. Well, if we want it to be absolutely convergent, that means not only the alternating series must converge, but also the non-alternating series must converge. And so we can kind of ignore all these alternating pieces and just focus on this. Okay. I'm sorry, I'm off the screen. You can ignore the alternating pieces because we're only interested in which one is absolutely convergent. So we want to know which one of these just actually converges here. Okay? And so we have n to the 1. I'm out of time. Okay. So this one, it's letter D. Okay? And then letter F converges absolutely. And we can finish going over these tomorrow. Okay.
See your paper.
Yep.
You said tomorrow?
Sorry, Monday.
Yeah.
Homework will be posted to Google Classroom. Okay.
We have homework over the weekend?
Yes, sir. Especially for all my little procrastinators that didn't do their homeworks last night or the night before.
Nice.
Yes.